Hello everybody, and welcome to example 2 on page 136 of the workbook. And this is going to be our first example of examining a function of two variables in an applied situation. Now let's take a minute and just read the first part of this problem together. So they're telling us that the temperature, T, in degrees Celsius at a point on a metal plate is given by the function T equals f of xy. Okay, so if you look over here at the picture, the metal plate you can picture as being kind of this grid, okay, that we have here. It's 8 by 8. And so x and y are kind of telling us where we're at on this metal plate, and then the vertical axis is giving us temperature. Okay, and you can see we've got a surface that represents the temperature. That's the T equals f of xy. And so maybe just to ask you a conceptual question to get this started, can you see where the greatest temperature is from this picture? That's like asking you, where does the surface reach its highest value? You can kind of see that that appears to be in the center here, which is telling us that down here on our metal plate, we should be getting the warmest temperature right at the center point. Okay? So let's go farther with this. Next sentence starts with our goal is to discuss the problem of finding the rate at which the temperature of the plate changes. Okay, we're going to talk about that rate of change in two different directions, in either the x direction or the y direction. Okay, let's talk about that conceptually. Okay, so I'm going to, just to avoid cluttering our diagram up here, I'm going to get rid of some of the stuff that we marked with here. And we'll pick a point to talk about, just to have a specific point. So I'm going to call this point that's already labeled for us AB. Okay, and we're going to talk about these rates of change one direction at a time, starting with the x direction. Okay, well, what we mean by the x direction is that we're going to move in the same direction as the x-axis. Okay, the x-axis is sitting here, so we'd be moving kind of in that direction. All right, so if we started at the point AB and moved kind of parallel to the x-axis, it would take us in this direction. And if you go up to your surface, if you move in that direction along the surface, does it look like we're going up or down? Okay, to me, it looks like the temperature would be decreasing. If we were kind of a bug walking along the surface and we moved in this direction, we'd be going downward. And the question is, how fast are we going down? Okay, well, we could answer that question by drawing in kind of a tangent line here. Okay, I'm going to label that line L1. The slope of that line would essentially measure how fast the temperature is decreasing, okay, as we move in the x direction away from the point AB. So let's put a little bit of notation to this. Okay, so our notation for the rate of change in the x direction is going to look like this. Tx of AB, the derivative of t in the x direction at the point AB, if we write out the words. Okay, and graphically, it's going to be the slope of that red line that we drew in. Slope of L1, and when I say slope, I mean change in temperature over change in x. Those were the only two variables that were involved, and y was actually constant. Okay, y wasn't changing because we were just moving in the x direction. Okay, and recall that we made the observation that it looked like that rate of change was negative because we were going down on our surface as we move in that direction. Okay, so we'll just make the comment that this derivative appears to be negative. Okay, now let's repeat that whole process, okay, and ask what would the rate of change of temperature be in the y direction? Okay, well, we would start again at our point AB here, but this time we're going to move parallel to the y-axis and ask the same question, what does it look like our temperature function is doing if we move in that direction? Okay, well, in the y direction, we'd be starting from up here, and we'd be kind of moving this way. And what do you think? Does it look like we're going up or down? If we kind of move on our surface in the y direction, it looks to me like we're going up a little bit at least. Okay, you can kind of see that if you draw a tangent line, it would sort of look like maybe that, just very slightly going up. Okay, and the slope of that line would be what we'd call the derivative of t in the y direction. Okay, so let's write that down. Okay, that's going to be the slope of the line L2, the change in temperature over the change in y with x held constant. Okay, we kind of looked at our picture and convinced ourselves that it looks like y is going ever so slightly up, so it would appear that this derivative that we've got is positive. Okay, well, it turns out there are names for these two derivatives that we wrote down. They're called partial derivatives of temperature. Okay, we use the word partial because we're taking the derivative with respect to just one input variable at a time. Okay, so I'm going to make that as a note, kind of at the end of this example here. So tx and ty are called partial derivatives. And let's remind ourselves of what those partial derivatives represent. They just measure the rate of change of temperature, okay, with respect to which direction we're moving in. Okay. And as we go further in this section, we will start to talk about how we might calculate derivatives like this or estimate them.